Okay, today we are looking at the third species we're taking the pH of, and that is of salt solutions. We call it hydrolysis for a reason, which I'll get to in a minute. But first, I want to compare different kinds of salts: acidic salts, basic salts, and neutral salts. So on this page, I'm just going to take a few notes. Starting out, I'm just going to write down the formula for 3 different salts. There's sodium acetate, and then we have ammonium chloride, and then HCl. Not HCl, sorry, NaCl. Good old table salt. Not all salts are the same. What do all salts have in common, though? They're ionic compounds, right. So looking at this first salt, one thing I want you to realize characteristically about all salts is they all come from parents. You guys learned a reaction when we did reaction prediction that when you add 2 things, you always get a salt plus a water. What type of reaction was that? An acid plus base makes a salt and water. So every single one of these salts come from an acid parent and a base parent, okay? The way I'm about to show you to figure out the range of acidity, this is kind of the Chem 1 way you learned how to figure out which, if the salts were acidic, basic, or neutral, and that's to look at their parents. So looking at this guy, what basic parent do you think made him? NaOH. And what acidic parent made this guy? Yeah, acetic acid. So if you want to kind of guesstimate the strength of that salt in terms of acidic, basic, or neutral, compare the strength of the parents. What classify NaOH? What is that? Strong base, acetic acid, weak acid. So the strong parent basically dictates whether or not this is an acidic, basic, or neutral salt. So we're going to say this is a basic salt because this parent is basic. Now, what do I mean by basic salt? If I were to take sodium acetate and dissolve it in water, it would make a basic solution. Okay? So looking at ammonium chloride, you're going to have to stretch your brain a little bit here. It's not cut and dry, but we know that ammonium probably comes from what base? Ammonia. And what parent do you think the Cl- came from? HCl. So here we have a weak base parent but a strong acid parent. So this is going to be an acidic salt. So when you dissolve this in water, you're going to get a pH less than 7. What about NaCl? What parents made that? NaOH and HCl. So what can you tell me about the strength of those? They're strong, so they kind of cancel each other out. So this is going to be a neutral salt. And when you dissolve sodium chloride, if you go in the ocean, luckily it's pretty neutral. Okay? All right. So this is the Chem 1 way to figure out what's going on. The actual way is through something called hydrolysis. So I want you to kind of, don't forget about the parent thing, but I want you to take a moment and just think back to the salt itself. Okay? When you put this salt in water, it's going to dissociate into what 2 ions? Forget the whole parent thing. Just what 2 ions does that make? Na plus C2H3O2 minus. Now, due to something called hydrolysis, only one of these ions is actually going to react with water. Sodium plus, because it is one of those ions, and if you think back to your solubility rules, what can you tell me about group 1 stuff? They're always soluble. So what's basically going to happen when you put that sodium plus, it might react with the water and make sodium hydroxide, but then it's going to then dissociate and have Na plus again. So ultimately, that's going to not react with water at all. What's going to react with water is always the ion from the weaker parent. That's the rule. You always react the ion from the weaker parent with water through a Laurie-Bronsted reaction. So if we take C2H3O2 and react it with water, if we do a Laurie-Bronsted, what are we going to make? Move an H. H's have to move. Correct. H, C2, H3O2, and what? OH what? OH minus. Look what we made. OH minus. What kind of salt did we say this was earlier? A basic salt. That's really why it's a basic salt. It's due to the fact that the ion from the weak parent undergoes hydrolysis and creates a situation that's either going to be acidic or basic. Okay? This is a hydrolysis reaction, and this is what you guys are responsible for knowing how to write. So let's go to the next one. Looking at that, what two ions do we have? NH4 plus and Cl minus. Which one comes from the weak parent? No, not. We're not looking at the parents. Which ion comes from the weak parent? NH4 plus. We're going to take that part of the salt, and it's going to undergo hydrolysis. Cl minus does not undergo hydrolysis because it's going to end up being just a spectator when you put it in water. So when we do this, what products do we make? NH3 plus H3O plus. So notice what we made here. And remember, we said it was acidic. Okay, so this is the hydrolysis equation for that one. Now here, because we have both ions from strong parents, neither of these ions undergo hydrolysis. Therefore, it's just the pH of the water, which is a pH of 7. It's not that they're both fighting or whatever. They're not. They're just hanging out. They're not doing anything in the water. Okay, they're not reacting with the water. So does everyone understand when I say write a hydrolysis equation what I mean? Take the ion from the salt that's contributed from the weak parent and add it to water. So let's do a little bit of practice. These next three slides are just kind of a repeat. This is talking about NaCl. This is talking about ammonium chloride. This one's talking about sodium acetate. You can read over those later. And then that's calc, so I'm going to actually just teach you how to do those. So some types of questions you might be answered. Predict the products when KCN is added to water. All right, so KCN, first classify, is a, no, I don't want you to tell me anything but what it falls into. Is it a strong acid or base? Is it a weak acid or base? Is it a salt or is it a buffer? It's a salt. So because it's a salt, we know that it has to undergo hydrolysis in water. Which ion of these two is going to react with the water? Cn what? Minus. From here, we can answer the question, will the pH of the solution be greater or less than 7? We're going to know this as soon as we figure this out. So which way does the H move? Correct. HCN plus OH minus. And what did we make? OH minus. So is this greater than, less than, or equal to 7? Because it's basic. So these are the types of questions you may be asked. Okay? The hardest part is writing the equation, and it's really not that hard. Okay. Now, this is really an important thing. I need you to know the difference between a dissociation equation and a hydrolysis equation. Dissociation is when the salt hits the water, bam, what does it do? It splits. At that point, if it can undergo hydrolysis, the ion will. If the ion can't undergo hydrolysis, it just sits there. So this whole kind of process has two steps, the creation of the ions, then the hydrolysis. So when we start here, describes what happens, the dissociation, when that's added to water. So our salt in solid form is added to water, and what do we make? No. Cl minus plus, remember, it hits the water, we're dissociating it. Now the ions are available for hydrolysis if they can undergo hydrolysis. Yeah, if it's 100% soluble, we're assuming it's a single-headed arrow. And unless you know otherwise, go with the single. Write the write the equation which describes the acidic character of this. This is kind of telling you that, hey, this is the ion that undergoes hydrolysis. That Cl minus doesn't. So how do we write a hydrolysis reaction with CH3 NH3 plus. How do we write a reaction? Okay. And what do we make? Can pluses move to pluses? No. What do we make? Plus H3O plus. Did that describe an acidic character? Yeah. So that's all they want there. Okay. Then they say write the expression and calculate Ka. We're not actually going to calculate it because they didn't give us any flipping numbers, but we can do this. We can write a Ka, no problem. Do I include water? Nope. Why is this a Ka and not a Kb? Because it's got acidic character, okay? So keep that in mind. That's going to be an important thing in a minute, okay? I didn't mean to draw the arrow there. I meant to draw the arrow there. So that's why it is a Ka. Got it? All right, now, with all of this under our belt, now we can actually do these problems, finding the pH using rice tables. So, calculate the pH of a 0.7 molar sodium acetate solution. They give us the Ka of acetic acid. First thing you have to ask yourself, is this a strong acid or base? Am I taking the pH of a strong acid or base? No. Am I taking the pH of a weak acid or base? No. And what am I? I'm taking the pH of a salt solution. Yes. That's what I'm doing. This is a hydrolysis problem. The first step in a hydrolysis problem is to do a rice table. And what are we adding to water? The ion from the weak parent. Which ion is that? The good old acetate ion. We're going to add it to water. And what are we going to make? OH minus and acetic acid. Okay. Water is not included. Our initial concentration here is 0.70000. Now, before we actually finish this up and calculate the pH, I want you to think back to the Chem 1 way and look at the parents. Let's make a prediction about the range of pH on this guy. Sodium hydroxide was a parent and acetic acid was a parent. Which one's stronger? Sodium hydroxide, right? So what do we predict the pH to be? Greater than 7. So let's go ahead and hopefully that'll be the case when we're done, okay? So we're going to have to shift right. The beauty about all of these problems is we always shift right. And so we get 0.7 minus x, x, and x. Due to the nature of these weak ions in solution, they are reacting a little bit, so we can trump it. And this is negligible. Make note of that. Negligible. All right. Let's go ahead and now we can just jump in and do x squared over 0.7. There's something important here, so I need you to write your expression. Looking at your reaction, what expression are we going to write? Look at the reaction. What equals? K what? Kb is equal to OH minus. Why did you choose Kb? Because we're making OH in solution. I want you to notice a problem. They're giving us Ka. This is a huge issue in hydrolysis problems, and it's always going to be a problem. They gave us Ka of acetic acid. They basically gave us the Ka of the reverse equation. So we need to find the Ka of the conjugate, the Kb, I'm sorry, of the conjugate base. It's not hard. Take a gander. What do you think Ka times Kb is equal to? Just guess. Not 1, but what? 1 times 10 to the negative 14th, better known as Kw. All right? So our Kb then is actually equal to the Kw divided by the given Ka. So what you can do when you're solving for this to make life easier is just plug in 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. You can do that work within it and be totally fine. And that's equal to, I plug in my stuff from the E line, x squared over 0.7. So I end up getting x, which is equal to what? OH minus concentration. So when you're doing these, right or wrong, just use the concentrate. Forget the K's, because every chart you use has different number of sig figs. Just use the concentrations to find your actual sig fig. So we're looking for a 3 sig fig OH concentration here. What is x equal to? Louder? I can't hear you. 1.97 times 10 to the negative fifth. If I take the negative log of that, what am I solving for? What do I get? POH. So give me 3 decimal places to have 3 sig figs. Three decimal places, please. All right, so that is POH, but the problem's asking for pH, so 14 minus that is 9.295. Is that basic, like we predicted? It is. All right, so every hydrolysis problem, you take the weak ion, or salt problem, you take the weak ion from the salt, add it to water, put it in the rice table, and you always have to convert Kb to Ka or vice versa. Those are the two things that make these a little bit different. No questions? You want to try another one? Well, you really don't have an option. You're going to try another one. We don't need to do the one up here. I just want to do, why isn't this, where is the, I can't see. Where is it? Here? I don't even know. Okay, we're not going to do this one. Let's just do this one. Okay, so I'm just going to use this whole page for this problem. All right, this is a hydrolysis problem because we're finding the pH of what? A salt. All right, so we're going to start our rice table. To start the rice table, we're going to add which of those ions to water? NH4 is not an ion. NH4 plus water. All right, what do we make? NH3 plus H3O plus. One piece of information that you will need to look up will be some sort of K, and I'll just give it to you. The Kb of ammonia is the same as the Ka of acetic acid. Kind of weird, but that is our Kb of ammonia. So we'll use that in the problem in a bit. So our original concentration then is 0.77700. Minus x plus x plus x. We get 0.777 minus x. We're going to drop x because it's negligible. X and x. Let's write our expression first. K what? Look at the equation. Ka is equal to NH3 times H3O plus divided by NH4 plus. But did they give us a Ka? No, they gave us the Kb of ammonia, of the conjugate. So we're going to say that the Kw divided by the Kb is going to be equal to that. So I'm just going to go ahead and plug that in. And so I get 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th is equal to x squared over 0.777. X then is equal to, well, it's a concentration, so 2.08 times 10 to the negative 5th, and that's also equal to what? H plus. So if I take the negative log of that, I straight up get pH. So give me 3 decimal places. 4.682. So this is acidic. Let's look back at the salt. Does acidic make sense? We have the parents of ammonia and HCl. Does acidic make sense? Yeah, it does. Okay? All right, for those of you here, I want you to work, well, hold on, let's talk about this one. What's the pH of KCl? Why'd you say 7? That's correct. Yeah, the parents are both strong. Those ions do not undergo hydrolysis. What I want everyone to do is work on this problem. I'm going to give you the Ka value for acetic acid. This is going to be on your own, and that is equal to 1.8, again, times 10 to the negative fifth. All right, so start working on that. For those of you at home, I want you to work it on your own, and your final pH answer then is going to be 9.179. So if you're at home and you don't get that answer, come see me.